Hi everyone. Today we are starting section 4.4, the mean value theorem. This is one of the most important ideas in calculus because it connects two big ideas, the average rate of change and the instantaneous rate of change, which is the derivative. In simpler terms, it helps us understand how a function behaves over an interval and how slopes relate to each other. So why do we care about this? There are three main reasons. First, it helps us understand how functions behave between 2 points. Second, it connects the average rate of change, like the slope between 2 points, to the instantaneous rate of change, the slope at a single point. And third, it has lots of real-world applications, especially in motion like speed and velocity. Now, before we get to the mean value theorem, we start with something called Rolle's theorem. Rolle's theorem is actually a special case of the mean value theorem, or a simpler version. Here's the idea. If a function starts and ends at the same value, meaning the height at the left endpoint is the same as the height at the right endpoint, then somewhere in between, the graph must flatten out. In other words, there is at least one point where the slope is zero. So we can say there exists a point C where the derivative at that point is zero. Let's make it more precise. Rolle's theorem works if three conditions are true. First, the function is continuous on a closed interval from A to B. That means no breaks, no holes, no jumps. Second, the function is differentiable on an open interval from A to B. That means the graph is smooth, no sharp corners. And third, the function has the same values at both endpoints, which is f of A equals f of B. If all three of these are true, then we can guarantee there is some number C in between A and B such that the derivative at that point is zero. Now let's look at the graphs to really understand this. From the first graph, look at the endpoints. This is where x equals A, and this is where x equals B. This is f of A, and this is f of B. F of A and f of B have the same height, so f of A equals f of B. The graph goes up, then comes back down. At the very top, the graph is flat. So there is a horizontal tangent line. That means the slope is zero there. So this is exactly what Rolle's theorem guarantees. There is a point C in between A and B such that f prime of C equals zero. From the second graph, again, the endpoints have the same height. The graph goes down and then comes back up. At this point, there is a horizontal tangent line. So the slope here is zero. This shows that there is some number C in between A and B such that f prime of C equals zero. From the third graph, this one is a little different. The endpoints f of A and f of B are still the same height, but the graph wiggles. It goes up, then down, then up again. Because of that, there are actually two flat points, one at the top and one at the bottom. So we have 2 points, C1 and C2, where the slope is 0. This shows that Rolle's theorem guarantees at least one such point, but it could be more. So the big idea from the graphs is this. If a function starts and ends at the same height, then somewhere in between, the graph must flatten out. It might happen once or more than once, but it has to happen at least once. An important note to remember, if a function is not differentiable at some point, for example, if there is a sharp corner, then the Rolle's theorem may not work. So we always have to check the conditions carefully before using the theorem. To summarize, if a function is continuous, smooth, and starts and ends at the same value, then somewhere in the middle, the slope must be 0.